Welcome. Welcome to Fudan Logic Sum School, and we are very happy to have our lecturers, Gabriel Goldberg from UC Berkeley, and in this week he will talk on the large cardinal beyond choice, and I think maybe many people know Gabe. He graduated from Harvard University and Hugh Wooding, and he worked on large cardinals and in the model theory. And among many other works, he isolated action known as the ultra power action. And he proved many significant consequences concern Wooding's Hall conjecture and ultimate L conjecture. Actually, he published a book. And Gabe, please.
Thank you. Thanks for the nice introduction, and thanks for inviting me to speak. And again, I'm sorry I couldn't be there in person, but I am waking up quite early for this talk, so you can't be that mad at me. So today I want to talk about, choiceless large cardinals. I just want to outline what I'm going to do over the next week. Maybe I'll say some things that you don't totally understand every detail of at this point, but that's okay. And of course, feel free to stop me with questions if you have any questions. I mean, even just vague questions. I'm desperate to get some questions. So I'm going to talk about first the limits of the large cardinal hierarchy in the context of the axiom of choice. So this is something called the Kunin inconsistency theorem. So I'll talk about it more later, but the idea is that large cardinals are formulated in a certain way, and if you just keep pushing that kind of formulation, you are inevitably going to wind up at an inconsistent principle. And the inconsistency, actually, it doesn't have to do with the more logical axioms of ZFC. It really has to do with the axiom of choice, which puts us in a sort of strange position because of the, I don't know, historical controversies about choice for other reasons too. Okay, and then I'm going to talk about large cardinals that go beyond the axiom of choice. So if you drop the axiom of choice, you can keep formulating large cardinal axioms in this paradigm, and it seems like they just extend the usual large cardinal axioms. Sort of a surprising thing that there are no known barriers on the large cardinal hierarchy except for the axiom of choice. And the last thing I'm going to talk about today is the structure theory of embeddings from V to V. So embeddings from V to V, this is like the sort of bottom of the hierarchy of large cardinals beyond choice. So this will be a big part of what we talk about this week. And I'll just sort of outline the results I want to talk about. Okay. So first, what are large cardinals? I'm not actually going to say in any precise way, but we have a natural hierarchy of theories that extend and strengthen the ZFC axioms. So you can think of large cardinals, especially the smallest of them, as just being sort of the next natural principles after ZF or ZFC. So for example, an inaccessible cardinal, I just learned how to write on the slides, so I'm very excited about it. So a kappa is inaccessible. This is sort of the smallest large cardinal. If V kappa, so I hope you know what V kappa is a model of second order set theory. So it's just saying that there's some level of the universe of sets that already satisfies the ZF axioms. It's hard to really I don't know, there are only so many ways you can extend ZFC, and it seems like large cardinals are really the only way beyond these axioms. Even some of the axioms of ZF sort of naturally fall into this paradigm, like they are themselves sort of large cardinal axioms, even though they are the axioms we're assuming. For example, replacement and power set really have sort of the form of large cardinal axioms in some sense. Okay, so what is the use of them? Well, on the one hand, whenever you're working in higher set theory, you run into theories that are so strong that their consistency cannot be established in ZFC. It's a little bit like the way that, well, the consistency of ZFC, for example, can't be established in ZFC. But it can be established if you assume the existence of an inaccessible. It's sort of a trivial example. But much more generally, every natural theory that has ever come up in practice, it seems, can be analyzed in terms of large cardinals. So we can find large cardinal axioms strong enough to build models of the theory or prove the consistency of the theory, depending on your perspective, or but also we can take the theory and use it to build models of the corresponding large cardinal axioms. So you can sort of exactly pinpoint the large cardinal axiom that's necessary for the theory to be proved consistent. So this is called the consistency strength analysis of a theory. So sort of our picture of the structure of theories, mathematical theories, especially foundational ones, so theories that set theories, but all kinds of set theories, is that they're sort of pretty well ordered by their large cardinal strength, by the large cardinals necessary to analyze and prove their consistency. But another and maybe less subtle application of large cardinals is that they can be used to provide a theory of sets that goes beyond ZFC. And they have interesting and highly non-trivial consequences for the structure of sets. So here are a couple examples. Kappa is strongly compact. You'll hear more, I guess, about strongly compact cardinals at some point in this series of talks. Then for all singular strong limit cardinals, the generalized continuum hypothesis holds at lambda. So this is a theorem due to Solovay from, I think, the 1970s. So you can prove instances of the generalized continuum hypothesis from the existence of large cardinals. So strong compactness is kind of large cardinal, but, well, it's one of the earlier large cardinals introduced. It was first discussed in work of, I think, Tarski in the 1940s or 50s. It wasn't for almost 20 years that this kind of structural hypothesis, the structural consequence was realized. And strongly compact cardinals especially have many combinatorial consequences. For example, maybe less famously, the failure of the square principle. It's a sort of consequence that you can't get without large cardinals. And let's see, then another sort of orthogonal thing is the determinacy consequences of large cardinals. So let me start writing in another corner of the slide. So also large cardinals imply regularity for definable sets of real numbers. So large cardinals have consequences in third order and second order arithmetic. For example, every definable set of real numbers is measurable. So this is something that cannot be proved in ZFC. Well, depends on what you mean by definable, but here, if you just mean definable over the real numbers with a predicate for the natural numbers and the basic structure on n, then you cannot prove that every definable set of real numbers is Lebesgue measurable in ZF or ZFC, but you can prove it from, say, a strongly compact cardinal, and actually much less. So even the basic theory of real numbers, which seems to be the correct theory, is given by and requires large cardinal axioms. Okay. So I want to talk about the problems, I guess, with the large cardinal picture of set theory. So we take ZFC to be our foundational theory, but we also want to say that large cardinal axioms are foundational principles. They're the principles we're trying to use to build up the theory of sets beyond what can be done in ZFC. But if you keep formulating these large cardinals, I mean, okay, so large cardinals, they sort of lie in a hierarchy of strength. So that there are weaker ones like inaccessible, and then measurable cardinals, which I hope you know something about. And then they get stronger and stronger, strongly compact. Things like huge cardinals and hyper huge, and I don't know. But one interesting aspect is that they form this linear hierarchy of strength, and you can keep strengthening them, and there seems to always be a natural way to get the next large cardinal axiom, but at some point you produce something that unfortunately is so strong that it refutes the axiom of choice. So it seems like we're getting these combinatorial consequences of large cardinals for a while, like the SCH. I mean, the instances of the generalized continuum hypothesis, which is called SCH, and then the failures of square, these determinacy hypotheses, and then eventually the combinatorial hypotheses you start getting are not ones that sit well with you. They're saying things like the axiom of choice is false, and false in these very strong ways. So one issue here, even besides so this is looking back to the methodology of large cardinals. Large cardinals, I said they could be used to prove the consistency of any natural theory. So the way we understand whether a theory is consistent is always relative to large cardinals. So if we want to know that some combinatorial set theoretic principle is consistent, the best and only way we know how to argue for that is by proving its consistency from a large cardinal axiom, typically by forcing. So you start with your large cardinal and you sort of, I don't know, massage it into your combinatorial principle by using Cohen's forcing method. But these large cardinals beyond choice, the large cardinal axioms that seem to contradict choice, if you just look at them as theories like ZF plus your large cardinal axiom, which refutes choice, it seems to be a consistent theory, but we can never hope to prove the consistency of these theories using the standard large cardinal axioms. So even if you say, I don't think that these a large cardinal axiom that refutes my foundational theory, ZFC, should count as a large cardinal, you're still in a tricky position because you have no way of gauging whether the theory of ZF with the pseudo choiceless large cardinal axioms is a consistent theory. So I'll say a little more about that later. That was confusing. And moreover, it is a sort of striking that the choiceless large cardinal axioms, like the large cardinal axioms before them, it's not just that they imply the failure of the axiom of choice, they actually sort of start to, I don't know, form this picture of sets that goes beyond what the old large cardinals can do. And in many ways, the theory at this level is starting to show even deeper combinatorial consequences than the large cardinal axioms at the levels below. But it's not at all clear what the picture is revealing. So, well, I mean, I'll talk in a second about determinacy axioms. And say the choiceless, I don't know, the choiceless large cardinal hypotheses, if you're not going to take them to be foundational, if you're going to say, well, these are consistent maybe, but they don't describe the true universe of sets, because I think that the axiom of choice should hold in the true universe of sets or something like that, then you're left with these principles that are describing some structure, but it's not clear what the structure is. And so it's hard to, again, it's hard to know whether to think that the principles are consistent at all, because you seem to just have a theory with no interpretation, unless you're going to go with an interpretation which is sort of sometimes treated as a little crazy, I've noticed, which the interpretation that these choiceless large cardinal axioms are true and the axiom of choice is false. So let me start to say some slightly more specific things about large cardinals, give you some actual definitions. So the elementary embedding paradigm for large cardinals was, I don't know, initiated in the late 1960s by Solovay and Reinhardt. The idea is, well, it comes from this theorem of Scott that characterizes measurable cardinals in terms of elementary embeddings of the universe of sets. So this is a theorem, it requires the axiom of choice. So a measurable cardinal, maybe you already know the definition, kappa's measurable if there is a kappa complete non-principal ultrafilter on kappa. But Scott showed that there's this sort of elegant, although I don't know, very, very abstract characterization of measurable cardinals in terms of elementary embeddings of the universe of sets V into a transitive model M. So the characterization is just kappa is measurable if it's the critical point of such an elementary embedding. So let's see, the critical point of an elementary embedding is just the least ordinal, such that J of alpha is greater than alpha. So let's see, have for any such elementary embedding, you always have that the power set of kappa, or even the whole structure V kappa plus 1 is contained in the inner model M. And well, this, I don't know, this is some kind of relic or typo. I don't know why I wrote this here, sorry. So V kappa plus 1 is contained in M. The way one typically strengthens axioms or produces more large cardinal axioms in the elementary embedding framework is by strengthening the amount of resemblance one has between V and M. So for example, kappa is a 2 strong cardinal if you can additionally find an embedding such that V kappa plus 2 is contained in M. So V kappa plus 1 is automatically contained in M, but V kappa plus 2 being contained in M is gives you a much stronger principle. So let's see, what should I say about this? I mean, so this is going to be on homework, I guess, homework exercises. If kappa is too strong, then kappa is a limit of measurables. So you get a strictly stronger principle by increasing the resemblance between V and M. Okay, so sort of jumping way higher in the large cardinal hierarchy, cardinal is super strong if not only is V kappa plus 2 contained in M. In fact, if you take all of V kappa and you move it under J, you get the true V sub J of kappa. So for an arbitrary elementary embedding, it is true that J of V kappa is the Vj of kappa that the target model M computes. So this is the same as Vj of kappa as computed in M. So it's just the sets in M that have rank less than J of kappa. So this includes, for example, the V kappa plus 2 of M. And if you assert that this embedding is witnessing that kappa is super strong, so this is actually equal to the true Vj of kappa, then you're also asserting that V kappa plus 2 is contained in M, and V kappa plus 3 and V kappa plus 4, but a huge amount more. So super strong cardinals are very strong principles. Let's see, for example, and I think this is also supposed to be on the homework. It's kind of tricky. If kappa is super strong, then V kappa satisfies that there is a proper class. Well, okay, so one thing is kappa is a limit of 2 strong cardinals, but something much stronger than that actually holds. V kappa thinks, well, both ZFC, because kappa is measurable and therefore inaccessible, but also there's a proper class of strong cardinals. So I didn't define a strong cardinal here, but a cardinal is strong if it's if for all lambda greater than kappa, there's J from V into M with critical point kappa and v lambda contained in M. Okay, so super strong is stronger than strong. Okay, but you can keep iterating this to get even stronger axioms. So n-fold super strong says that if I start with v kappa and then I move it to using j to j of v kappa, well, first this is equal to v sub j of kappa. But then if I move it again using j to j of vj of kappa, this is actually equal to v sub j of kappa. And I can do that again and again and many times. Okay, these are starting to be some of the stronger axioms in the large cardinal hierarchy, at least in the ZFC large cardinal hierarchy. So you're sort of just generalizing some pattern that started at super strong in a natural way, and it's giving you this hierarchy of principles that you just get stronger and stronger. So any n-fold super strong cardinal is a limit of n-1 fold super strong cardinals, etc. So you can't, though, just keep doing this forever. So Kunin showed, again, let me emphasize that this is really requires the axiom of choice, that there is no non-trivial elementary embedding from V to V. So this is somehow the limit of this this paradigm for formulating large cardinals. We're saying that V, or we had been trying to strengthen these principles by saying that M, this inner model, is bigger and bigger. It's resembling V more and more. But you can't just keep strengthening it forever and say that that M is just equal to V, because if you do, you run into a contradiction. Okay. So actually, the limit of the large cardinal hierarchy in CFC is much lower than an embedding from V to V. So let me just try to describe where it actually lies. So here's just some useful notation. So if you have an elementary embedding between two models, P and Q, you can start at the critical point of the embedding J and move it up by a J to J of kappa, or what I'm calling kappa 1 of J. And then you can do it again and move kappa 1 up to kappa 2 of J, and so on. Okay. And then if you take the limit of this process, you get this ordinal kappa omega of J. And if, so you can, one thing to notice is it's possible that at some point kappa n is not actually an ordinal in this transitive set P, and then this process would break down and you wouldn't be able to define the kappa n's anymore. So there's sort of an assumption here that that the process doesn't break down, so that all the kappa n's are in P. And this is going to happen pretty often for us, because this model P will often be V, and V has every ordinal in it. Okay, so the thing about kappa omega, if it is in P, is that it has to be, well, should be a fixed point of the elementary embedding J. So that's actually not necessarily true. It's useful to try to find a counterexample to that, but in all the examples we'll be looking at J of kappa omega is equal to kappa omega. And the reason, roughly, is that J of kappa omega is equal to, well, it's J of this supremum of the kappa n's. And sort of by elementarity, this supremum should be the supremum of the j of kappa n's. And this should equal, well, the supremum of the kappa n plus 1s, which is again just kappa omega. So this, this step sort of requires some hypotheses on j. Some to go from here to here requires that j is continuous, really, at the supremum of the kappa n's, which won't happen for an arbitrary elementary embedding, actually, but it will happen whenever we care. So an n-fold superstrong cardinal is just a cardinal that's the critical point of an elementary embedding that contains the v kappa n of j. Well, that contains v kappa n of j. That's it. So so these points, so this is called the critical sequence of j, sort of help us give a more, I don't know, quick definition of the n-fold superstrong cardinals. Axiom I2 asserts, so I know I2 is sort of a weird naming convention, like it's especially weird if you don't see what either I1 or I3 are, but this thing was named axiom I2 in a famous paper from the 1970s. It says that there is an omega fold superstrong cardinal. So an elementary embedding from V into an inner model M of ZFC, with critical point kappa, such that V kappa omega of J is contained in M. So that is beyond all these n-fold superstrong things. So kappa will be a limit of n-fold superstrong cardinals for all n. And it turns out that this is almost the edge of what is consistent with ZFC. So Kunin showed that there can't be omega plus 1 fold superstrong cardinals. So you can't have an elementary embedding from V to M with the property that V kappa omega of J plus 1 is contained in M. So this is really a much sharper version of the theorem that there's no J from V to V, because if J is an embedding from V to V, then of course V kappa omega of J plus 1 is contained in its target model, because everything is contained in its target model. And I think it is pretty surprising, because we just have this natural sequence of principles that seems to be getting stronger and stronger, and each one is just generalizing the last one. And this is sort of the thing you do at other levels of large cardinal hierarchy. Well below this, even below a super strong, there are sort of hierarchies like this within the large cardinal hierarchy, and everything just works out fine. You keep generalizing and the large cardinals get stronger, but they're not just inconsistent. So this, I think, was disturbing to people. I mean, the story of these principles at the beginning is that Reinhardt, who was sort of responsible for the development of many of the large cardinals coming from the elementary embedding paradigm, he actually proposed in his dissertation as an axiom the principle that there's a J, an elementary embedding from V to itself. So Kunin then, I don't know, a year or two later, refuted this principle outright. So there genuinely was one of these very strong large cardinal axioms that was just refuted. And I think that I don't know, that scared people. And so people have sort of stuck to large cardinals below this level or right around this level to try to And I think there's been a feeling that maybe something like this could already be inconsistent. So how do you really get to the edge of what is consistent with ZFC? Well, there's another way to climb up the large cardinal hierarchy. So instead of looking at embeddings from V to M, you can look at embeddings from levels of V, so V alphas into V betas. So for example, if you have one of these omega super strong, omega fold super strong cardinals, you can restrict it down to V sub lambda, where lambda is kappa omega of J. And what you get is a non-trivial elementary embedding from V lambda to itself. V lambda is a model of ZFC. Well, I'm assuming ZFC holds in V. So this seems like very close to the Kuhnian inconsistency, the result that there can be no J from V to V, but notice that that V lambda, along with it satisfies. I mean, you could ask how could Kuhnian's theorem even be true, since we have this model V lambda with this embedding J, and V lambda is a model of ZFC. Why can't I just apply Kuhnian's theorem in V lambda and refute the existence of an embedding J from V lambda to V lambda? And the point is that V lambda along with J is not a model of ZFC. Because J, if you have, so what does this mean? V lambda J is not a model of ZFC. It just means that the replacement axiom fails if J is allowed as a predicate. So remember, the replacement axiom says that the image of a definable function on a set is always a set. But now, if you allow J as a predicate in the definition, you no longer have the replacement axiom in V lambda. And the reason is that allowing J, you could define by recursion the sequence of kappa n of J's for n less than omega. And this is not a set in V lambda because it's cofinal in the ordinal lambda, so it doesn't have ranked lambda. Okay, so this is sort of the first level of the hierarchy of embedding axioms from a rank to itself. They're called rank to rank axioms. You can actually go up one more level, which is a little surprising. Remember, Kuhnian's bound said that you couldn't have an embedding J from V to M such that V kappa omega of J plus 1 is contained in M. But you can have, or it seems to be consistent with ZFC, and there are good reasons to believe that there's a major difference between this and this. You can have embeddings from V lambda plus 1 to V lambda plus 1. So this is called the axiom I1. So the weird naming conventions actually come from this paper by Solovey, Reinhardt, Kanamori, which is worth looking at. So they discuss the axioms, the limits of the ZFC large cardinal hierarchy, basically the topic of this part of this talk, and they introduce these principles. So I3 is an embedding from V lambda to V lambda, and I2, well, it's, as I said, it's this omega fold super strong. and I1 is an embedding from v lambda plus 1 to v lambda plus 1, you can show that I3 is strictly weaker than I2, which is strictly weaker than I1. And I guess the reason for these conventions is that they expected a couple things. The I think stands for inconsistent. They don't say that, but they expected even this weakest one could be refuted. Maybe it's just some little tweak on the proof of the Korean consistency theorem. And then the numbering them in reverse order of their strength, that is a really strange choice, in my view, because I guess it shows the extent to which they thought you can't really get past something like I1. That there are no principles past there, because you don't, what if you had something stronger, you'd have to name it I0, and then if you had something stronger than that, you'd have to go into the negative numbers, which in set theory, there barely are any negative numbers. Okay, so
wait, sorry, can you explain again why I0? Yeah, I had a freeze, so I'm not sure what you exactly said, but you mentioned I0, so it's believed to be inconsistent now?
No, sorry,
okay.
I was only kind of joking.
Okay, yeah,
I was just pointing out that in 1970 or whenever they decided to name these, they really did think that these principles.
Oh, I see. Okay, now I see.
And that's why I think that's why they. I mean, I'm sort of speculating here, but I do think that that's why they named them I sub n, and I think that they're the fact that they were sure that they were inconsistent sort of
I see.
Have this weird
you thought that
normally you don't expect a large cardinal hierarchy.
You didn't expect,
going down. Okay.
Okay.
But okay, so even at this point, it was known that you can't assert the existence of an elementary embedding from p lambda plus 2 to itself. So even though this alternate way of formulating large cardinal axioms, where you assert embeddings from the v alpha to v alpha, did let us get slightly past omega fold super strong. It stops right here at I1, and the principles become inconsistent just as soon as you reach embeddings from v lambda plus 2 to itself. So it sort of led people to focus on principles that are just around v lambda plus 1. So let's see. I want to tell you about principles right around between here. This is I3 and here. So principle dn of lambda. So this is non-standard notation, but it's a principle that was studied by Tony Martin. The history behind these is kind of interesting, and I guess it's almost time for me to say something about the axiom of determinacy, because the first real study of these principles was at a time when people were trying to prove the consistency of the axiom of determinacy. So this is the 70s and 80s, and it was unknown whether even the lowest levels of definable determinacy beyond analytic determinacy were consistent, and determinacy was thought to be stronger than all the large cardinal axioms. And people started developing an analogy between determinacy principles and actually these very strongest, the strongest axioms there are. So these dn of lambda principles are sort of can be thought of as analogs of projective determinacy. So I'll tell you, I guess, about projective determinacy. Well, I might as well say it now. So I don't have a slide on it, but I can just tell you. So it's possible to give a pretty simple model of two-player games of perfect information. So you have two players, 1 and 2, and they alternate making moves. You can assume their moves are drawn from some finite set or even from the set of natural numbers. It won't really make a difference for what I'm saying. So each one plays on the first move some number, 2 plays on the second move some other number, and they alternate like this until maybe at some point they stop and they've produced some string of numbers. And then you want to say, so this determines the play of some game, and you want to say who wins. So you can think of this like chess, and the natural numbers are some natural way of encoding what piece is moving to what other piece. I mean, what piece is moving to which square. You want to say when does a sequence of moves constitute a win for player 1, and that will describe a 2-player game, right? So the set of winning plays. For 1 describes a 2-player game. So hopefully you've seen something like this before, because otherwise I think this is possibly a very confusing introduction. Okay, so Zermelo showed, maybe not totally abstractly, but he showed that in any game like this, any finite 2-player game, perfect information, one player has a winning strategy. So this is a way of playing in the game that always forces a win. So say 1 has a winning strategy if there's a way for 1 to play, so that no matter how 2 responds, when they reach the end of the game, they always reach a winning play for 1. Yeah.
Sorry, that assumes that one of the player must win, right?
Yeah. So there's a set of winning plays for 1, and then everything else is a win for 2. Yeah. So in chess, where there are draws, it could be instead that it's just that either there's a winning strategy for 1, or there's a drawing strategy for 2. Okay, so in other words, I mean the terminology is that any finite 2-player game is determined from the beginning of the game. Who will win is determined, at least if the players have play optimally. We know who wins from the start. So the axiom of determinacy, well, it's the generalization of this Zermelo theorem from finite games to infinite games. So if you think about the proof of the Zermelo theorem, it's kind of a surprising fact, I guess, at first. For example, that there's a perfect way of playing in chess, when we sort of know intuitively that you can't really play chess perfectly, or I can't at least. But the point is that if 1 doesn't have a winning strategy, then 2 can win the game just by always playing so that 1 continues not to have a winning strategy. So if one doesn't have a winning strategy, then one makes the first move, and now two can find some move so that from the next point on, one still doesn't have a winning strategy. And if two continues like this over and over, then one can never win the game. And since we know the game has to eventually end, that means that this way of playing for two has to be winning. Okay, so that's a sort of vague proof, but it really relies on the fact that it's a finite game. So you can also consider games where the play goes on forever. So the two players never stop playing. And so at the end of the game, what they'll have produced is not a finite sequence of numbers, but instead an element of the bare space. So together they're going to produce this, I don't know, in logic, you call it a real number. Okay, so it's an element of bare space, or however you want to think of it. It's in omega to the omega. Each of these moves is supposed to be a natural number. Okay, so you can still define, given a set A contained in bare space, you can say that one wins this game associated to A if the play that they produced is in A, and otherwise we can say two wins. And you can ask, is a game like this an infinite game determined? So does one or the other player have to have a winning strategy? So this would be a way for, say, player one to play, so that no matter how two responds after infinitely many moves, the real X that's produced is an element of A. Or for two, it would be a way of playing so that after infinitely many moves, no matter how one has played, the element of bare space they produce is not an element of A. So turns out that, well, first the axiom of determinacy. So infinite games like this were, I think, studied first by like the Polish school of analysts and descriptive set theorists. And sort of striking thing was that many of the games they considered, even though they were infinite, they still had strategies for one or the other player. And also many regularity properties. Well, I'm not sure they knew this one, but for example, the bare property for subsets of the bare space could be formulated in terms of whether one or the other player has a strategy in this game or in a similar game. So the axiom of determinacy says that every A contained in omega to the omega is determined. So in other words, it's the infinite version of Zermelo's theorem. So in any infinite game of the two-player game of perfect information in which each player is playing natural numbers, either the first or the second player has to have a winning strategy. And the interesting thing, this was proposed by, I think, Michalski and Steinhaus. They proposed it to be considered as an axiom of set theory, but they did point out that AD implies that the axiom of choice is false. And in fact, the real numbers cannot be well ordered. Okay, so even though they propose this to be considered as an axiom of set theory, mostly when people have considered determinacy, they've considered the determinacy of definable games. So this will be related to what I'm about to talk about, I promise, even though this has been sort of a long digression. So sorry, this first lecture, there's some break, right, at 8 a.m. My time. Is that true?
Yes, there's still, I think there's still 20 minutes to break.
There's still 20 minutes before the break?
There's 1 hour and 15 for
1:15.
Okay, great. Okay. So the axiom, there's already a sort of an analogy between the axioms I've been mentioning. So these very large cardinal axioms around elementary embeddings from v lambda plus 1 to v lambda plus 1, and the axiom of determinacy. I guess at this point, it's just that the full axioms, the axiom of determinacy refutes the axiom of choice, and the full axiom, like a j from v lambda plus 2 to v lambda plus 2, refutes the axiom of choice. And in fact, it implies that v lambda plus 1 cannot be well ordered. So let's see. I think I've said as much as I should about determinacy, at least for a second. Hopefully, if you didn't understand anything I said about determinacy, you should still be okay throughout this course, but it is a very important thing. The analogy between determinacy and large cardinals is very important for the field of large cardinals at this level. So try to keep it in mind, but if you feel you can't, you had to start tuning out while I was trying to tell you about determinacy, I think you'll still be fine. Okay, so back to these principles that Martin was studying. So the principles dn lambda state that there's a sigma n elementary embedding from v lambda plus 1 to v lambda plus 1 with lambda the supremum of the critical sequence of the embedding. Okay, so the interesting thing that happens here is that these principles have this sort of strange and, in large cardinal theory, unprecedented periodicity pattern. So d0 of lambda, which is actually, so it says there's a sigma 0 elementary embedding j from v lambda plus 1 to v lambda plus 1. But as I say here, it's actually equivalent to this axiom I3 that I talked about before, just an elementary embedding from v lambda to v lambda. It's strictly weaker than d1 of lambda. Okay, d1 of lambda is equivalent to another principle we talked about before, just I2, so the existence of a j from v to m, such that v lambda or v kappa omega of j is contained in m. And but even though sigma 0 elementary embeddings are strictly weaker than sigma 1, in fact, sigma 1 elementary embedding, any sigma 1 elementary embedding from v lambda plus 1 to v lambda plus 1 is automatically sigma 2 elementary. Okay, but on the other hand, sigma 2 elementary embeddings are not necessarily sigma 3 elementary. When I say sigma 3 and sigma 2 elementary, I just mean preserves sigma 2 or sigma 3 formulas with parameters. So if phi is a sigma 2 formula, then v lambda plus 1 satisfies phi of a, if and only if v lambda plus 1 satisfies phi of j of a. So for example, sigma 2 elementary is equivalent to pi 2 elementary. But this this jump, the fact that sigma 1 elementary is equivalent to sigma 2 elementary is actually not obvious at all. And it can't be that obvious because, I mean, the proof has to involve some kind of subtlety, because the equivalence does not extend at this level. Sigma 2 elementary embeddings do not have to be sigma 3 elementary. In fact, the existence, if lambda satisfies that there's a sigma 3 embedding from v lambda plus 1 to v lambda plus 1, then lambda has to be a limit of cardinals lambda bar where d2 of lambda bar holds. So where there's a sigma 2 elementary embedding from v lambda bar plus 1 to v lambda bar plus 1. So there's this strict hierarchy of principles, but also these sort of interesting equivalences in between that come out of the blue. Certainly surprising to me when I learned about this theorem. And there is a kind of analogy here. It's not perfect, but so let's see. So delta, you can talk about delta 1 n determinacy. So this is the determinacy of sets that are delta 1 n definable in the structure B omega plus 1, or equivalently in the structure R with n and typical arithmetic. So I think maybe the better way to say this is in n to the n. Need some kind of evaluation function for elements of n to the n. So delta 1 n determinacy says that if you have a delta 1 n definable set, then it is determined. This is a principle in second order logic. It's first order expressible in the structure b omega plus 1. Similarly, dn is first order expressible in the structure b lambda plus 1. And we have this sort of interesting periodic equivalences. For example, delta 1 2 n determinacy is equivalent to sigma 1 2 n determinacy. On the other hand, delta 1 2 n plus 1 determinacy is strictly weaker than sigma 1 2 n plus 1. Sorry, I'm writing these little tildes that don't have a good explanation. So we have this sort of sequence of principles for the structure of that are giving you information about the structure of v omega plus 1, or first order in v omega plus 1. And there's also this periodicity in the logical relations in between them. So that I'm saying this, I mean, it's not a perfect analogy here. And there are places where the analogy is actually much stronger, but there really aren't a lot of theorems like this where you have an even odd dichotomy in terms of set theoretic definability. That doesn't happen very often in set theory. The only two places where this kind of thing has come up ever, I think, is in determinacy and in large cardinals at this level. Okay, so these principles, the DNs, are supposed to be an analog of the principles of delta 1n and sigma 1n determinacy. I think it's sort of an open problem how to exactly line up the DNs and the levels of what's called projective determinacy, which is just definable determinacy for this structure. So let's see. So these principles, the dn principles, they're all strictly below the principle I1, which remember says that there is an elementary embedding from v lambda plus 1 to v lambda plus 1. So again, we're still working in the context of ZFC. Necessarily here, you'll have to have that lambda is equal to kappa omega j. Right, you can just prove that lambda is kappa omega plus j if there's a j from v lambda plus 1 to v lambda plus 1, because otherwise, well, you can prove it using things I've already said. I said that you can never have an embedding from v lambda plus 2 to v lambda plus 2 for any lambda. Anyway, so it's an exercise that's worth doing, but the dn's are obviously below I1 just because dn asserts a sigma n embedding from v lambda plus 1 to v lambda plus 1, whereas I1 asserts a fully elementary embedding. So if I1 holds at lambda, then lambda is going to be a limit of cardinal lambda bar such that dn of lambda bar holds for all n. Okay, so d1 n of lambda asserts a sigma n elementary embedding from v lambda plus 1 equipped with a truth predicate for v lambda plus 1 to itself. So it's the next level of elementarity that's beyond all of the sigma n for n less than omega. You're giving yourself a satisfaction predicate. So if you're even just sigma 0 elementary from v lambda plus 1 with a satisfaction predicate to itself, it's basically the same thing as saying that you're fully elementary. So we have a hierarchy of principles that are now beyond I1 lambda. So and you have exactly the same kind of periodicity features that from the Martin theorem that I mentioned on the previous slide. And you can keep going. So sort of a little exhausting to keep going this way, but you can look now at embeddings from v lambda plus 1 s to itself, where s is the satisfaction predicate of v lambda plus 1 t, where t was the satisfaction predicate of v lambda plus 1. So you're just iterating the satisfaction predicates, and just as you get a hierarchy of higher definability as you iterate satisfaction predicates and definability with respect to them, you get a hierarchy of higher elementarity when you demand that these iterated satisfaction predicates are preserved by the elementary embeddings you're considering. Okay, so we have this picture. It looks actually a lot like the determinacy picture still. I mean, you can of course consider the determinacy principle, where you assert determinacy for everything that's definable in over v omega plus 1, along with the second order truth satisfaction predicate. So this is the same kind of thing. It's just, how do you extend these principles of elementarity? Well, you just go to higher forms of definability. Okay, sort of natural way to extend this into the transfinite is to assert embeddings from L alpha of v lambda plus 1 to itself. So L alpha, hopefully you remember the constructible hierarchy. You form the L alpha hierarchy over v lambda plus 1 by first looking at all the definable subsets of v lambda plus 1. So this is going to be L1 of v lambda plus 1. And then L2 of v lambda plus 1 is equal to the iterated definability over v lambda plus 1. So an elementary embedding from L1 of v lambda plus 1 to itself will be something like an elementary embedding from v lambda plus 1 along with its satisfaction predicate to itself, and so on. So these principles are, this is basically the generalization of these two. The L alphas are essentially the generalization of iterated definability using truth predicates over v lambda plus 1. This is the next natural place to go. And these are starting to get very strong. And then finally, the principle I0 of lambda is defined by Wooden in the 1980s. It asserts that there is an elementary embedding from L of v lambda plus 1 to L of v lambda plus 1. So that is, remember. So you have to say here that lambda is kappa omega of j. That's no longer a consequence of I0, even though at this level, lambda has to be kappa omega of j. It's sort of subtlety here. But anyway, Wooden's axiom is the same as asserting that for all alpha, well, here I really should have said lambda is equal to kappa omega of j as well. For all alpha, d alpha n of lambda holds. So it's just what happens if you start with a j from v lambda plus 1 to v lambda plus 1. You start demanding more and more elementarity for this embedding. And then you sort of iterate this through all the ordinals. Okay, just the, most natural way to extend this principle. So why was Wooden looking at the axiom I0? I mean, okay, the naming convention here, I think, is it's a reference to the old paper, obviously, where they named I3, I2, I1. And I0 is just much stronger than I1. The reason Wooden was looking at this axiom is that he was trying to prove the consistency of the axiom of determinacy. AD, so if the full axiom of determinacy, it was an open question at the time whether this was consistent with ZF.
Hey, Gabe.
Yeah.
Yep. Oh, sorry. Can I hold it? Like, your definition of D alpha.
Yeah.
To D alpha lambda. Oh, hold on a second. That is from L alpha v lambda plus 1 to itself, right? Shouldn't be L of J of alpha subscript.
Sorry, what?
Shouldn't be like L alpha v lambda plus 1 into L of J alpha v lambda plus 1.
Well, so are you saying,
Well, I mean,
could it be L sub J of alpha v lambda?
yeah, because when alpha is small, that's fixed. I mean, it's fixed by J.
You can always get any ordinal to be fixed by these kinds of embeddings.
Well, yeah, sure. You cannot have compounded embedding.
So it doesn't, yeah. So it doesn't really matter which way you state it. If you have,
yeah, what I'm saying just being inaccurate. Well, it doesn't matter. I mean,
yeah, I think
you notice that that's fine.
Yeah, I think it's fine to define it this way.
Okay.
It will make
yeah,
sense.
because you stated like for all alpha, D alpha and lambda.
Oh, but
so in that case, it might be careful.
No, this is still okay. This is still equivalent to I0. So it's not, because I'm not demanding that the D alpha ends all be witnessed by a single embedding.
Okay.
So it's okay, I think.
Okay, I see. Okay, sorry. for interruption.
No problem. No, thank you for the question. I am
There you go.
very excited to get a question. Okay. Yeah, so Wooden was trying to prove the consistency of the theory ZF plus AD. And there was this analogy between definable determinacy, so determinacy for definable sets and determinacy, and the large cardinal axioms like dn of lambda. And Wooden's axiom I0 seems to be roughly the large cardinal axiom analog of the principle that the axiom that every set of reals that belongs to the model L of R is determined. So L of R in that case, well, it's a model of ZF, and if every set of reals in L of R is determined, then it's a model of AD. So so Wooden actually was successful and proved AD-L of R. This is the first proof of AD-L of R from large cardinals, assuming the axiom I0. So he developed a connection between these embeddings and a direct connection, not just an analogy between these embeddings and the structure of sets of real numbers. So Martin had already been proved, I think, delta 1, 2 determinacy from a principle between I0, no, a principle that is in between I3 and I2. So so later Wooden proved the AD-L of R was a consequence of I0. And so there was sort of this picture that made it look like these very strong large cardinal axioms were actually not just analogous to the determinacy axioms, but exactly the principles that you needed in order to analyze the determinacy axioms. So that's a picture that turned out to be completely wrong. Just about a year later, the Wooden and Martin and Steele showed that much weaker large cardinal axioms imply these determinacy principles. And yet, what I'll talk about after the break is that this analogy between these very large cardinal axioms and determinacy is still very compelling, even though the strengths are completely wrong. So there's a kind of mystery there, which is part of what we'll be exploring in this course. Okay, so I think it's past time for the break. So what time do we resume again?
We have 15 minutes break.
Okay.
And I think we can come back from 33, right? Yeah, now it's
Okay.
18. Okay.
So, original plan is we have a half an hour break.
Half an hour.
Yeah.
Oh, sorry.
Half an hour break is good for me.
Yeah.
Okay.
So
Okay.
we should.
Okay.
So we should come back
Back
from
and
45?
45.
Okay.
45. See you.
Shall we start?
Okay, so as I was saying before, I now want to talk about the analogy between the axiom of determinacy in L of R on the one hand, and Wooden's axiom I0 of lambda and L of V lambda plus 1. So I should really say, how does this analogy work? Well, here we've got the natural numbers, or the structure V omega, and we have V lambda on this side, and they sort of play a similar role. Now the real numbers, or V omega plus 1, which for set theorists are roughly the same thing, play the same role as V lambda plus 1. And then the definable or the constructible subsets of R, the ones that belong to L of R, are playing the same role as the definable subsets of V lambda plus 1, or the constructible ones. But it turns out that there are sort of deep structural analogies between the two models that sort of are very hard to explain, because the proofs of these theorems that I'll show you are totally different. So here's a famous theorem from AD. So under AD L of R, omega 1 is a measurable cardinal in L of R. So this is part of the fact that so if AD holds in L of R, then the axiom of choice is false in L of R. So so AD L of R just means that L of R satisfies AD, of course. So AC has to fail in L of R. So remember the definition of a measurable cardinal, which was, I wrote it down before. Kappa is measurable if there's a kappa complete non-principal ultrafilter on kappa. So this is saying that there is an omega 1 complete, or countably complete ultrafilter on omega 1, at least in L of R. And actually, you can say exactly what it is here. This is the closed unbounded filter. So in the L of R, every subset of omega 1 either contains a closed unbounded set or is disjoint from one. That's what it means for this to be an ultrafilter. And it's countably complete. Well, that's just because the closed unbounded filter is countably complete in the true universe of sets. Okay, so an analog here for I0 is that lambda plus is measurable in L of V lambda plus 1. So, and again, it's not quite the club filter here. It's an open question. So in L of V lambda plus 1, the closed unbounded filter lambda plus is not an ultrafilter. It's just because there are many sets, there are many disjoint subsets of lambda plus that all are stationary. They meet every club. So for example, S lambda plus delta, the ordinal is less than lambda plus of cofinality delta. But it's an open question whether the omega closed unbounded filter on lambda plus is an ultrafilter. So it's a sort of interesting, an appealing strengthening of this analogy. Sorry, what I meant to say was that under AC, measurable cardinals are very large. They're inaccessible. And much more. In particular, they're much greater than omega 1. They can never be successor cardinals. So these theorems represent strong failures of the axiom of choice in L of R and L of V lambda plus 1. But it's sort of remarkable to have these instances of well-studied and quite strong large cardinal properties that just follow from this sort of logical seeming axiom with definable witness to the large cardinal axiom. Like here, it's the closed unbounded filter. Here, it's almost certainly the omega closed unbounded filter. So here's another example, maybe somewhat simpler. So in L of R, under ADL of R, the continuum hypothesis holds in the following sense. Every uncountable subset of the reals is in bijection with R. Actually holds in a stronger sense called the perfect set property, which is, it's a strong form of the continuum hypothesis that is incompatible with the axiom of choice. That's true in L of R. It's a generalization to all sets of Cantor's theorem that every uncountable closed set contains a perfect set. So this is how Cantor proves CH for closed sets. Under AD, it holds for all sets. Let's see. I want to say something else about this. I mean, I think, in fact, one has that AD implies this version of the continuum hypothesis. And I think it's worth noticing that this is a really, I don't know, beautiful, and it's a key application of AD. You actually prove the continuum hypothesis from this principle, which, you know, on the one hand, it's incompatible with choice, which is too bad, but it is a sort of logical seeming principle, this dichotomy. Either the first player has a strategy in this game or the second player does. It's sort of, I don't know, a logical seeming principle that that leads you to the continuum hypothesis. It's at least very interesting, even if its philosophical significance is maybe reduced by the fact that we can't assume AD as an axiom if we want to assume the axiom of choice. Okay, well, fairly recent theorem of Scott Kramer. I should say this is from the early 1960s, I think. And this theorem is from the 2010s. But it's the same theorem. Wooden's theorem about lambda plus being measurable is from the 80s. It's the same theorem in L of V lambda plus 1 version of the continuum hypothesis holds for V lambda plus 1. So every subset of V lambda plus 1 either has cardinality less than or equal to lambda, or else is in bijection with V lambda plus 1. So it's kind of remarkable to get this this version of the generalized continuum hypothesis. I mean, we're talking about real subsets of V lambda plus 1. It's telling you you really can't define an intermediate set. Now, of course, if there was a strongly compact cardinal below lambda, then you have the actual GCH 2 to the lambda is equal to lambda plus in V. But in L of V lambda plus 1, as I've been saying, that there is no well ordering of V lambda plus 1. So this is not a vacuous theorem even. Well, yeah, it's not a vacuous theorem even in the case where GCH holds in the true universe, because there could be sets that seem to be intermediate sets in L of V lambda plus 1, but it's just because the bijection isn't in there. Okay, so this is saying that, well, I guess it depends how you read what I wrote, but I mean that L of V lambda plus 1 sees that there's a bijection between the set of V and V lambda plus 1. So anyway, in a strong sense, and in fact, in the same sort of perfect set theorem sense, again, L of V lambda plus 1 satisfies the GCH at lambda. So I should mention the regularity properties. This is something that I sort of hinted at before. So AD implies, for example, that every set of reals is Lebesgue measurable. And Baire measurable, so it has the property of Baire. Well, there isn't really a great analog of Lebesgue measure for subsets of B lambda plus 1, but there is an analog of the property of Baire for subsets of B lambda plus 1. And at the conference I was at last week, I had learned that recently, I think as recently as this year or last year, the Baire property has been established by De Monte and Yanella for every subset of V lambda plus 1 in L of V lambda plus 1. So these regularity properties also transfer over to L of V lambda plus 1, this analogy. So sort of more structural properties of L of R and L of V lambda plus 1. So if a key characteristic of L of R and more generally of models of determinacy is the ordinal theta, which is the supremum of all the ordinals that are the surjective image of the real numbers in L of R. So in other words, theta is equal to the supremum of all alpha such that there is a function from the reals onto alpha with f in L of R. So Moskovakis proved that under AD L of R, theta of L of R is a strongly inaccessible cardinal in L of R. Okay, so I gave you a definition of strongly inaccessible before. Since L of R is a model of where the axiom of choice is false, the different definitions of large cardinals can come apart and stop being equivalent in L of R. So theta of L of R is not a strongly inaccessible cardinal in the sense I told you before, where the kappa is a model of second order set theory. So this is a different kind of strongly inaccessible cardinal. So instead, I only mean that for every eta less than theta, there's no surjection. Well, yeah, so here it says every function from P of eta to theta is bounded, which is equivalent to saying there's no surjection from P of eta onto theta, and theta is regular. So if you're familiar with inaccessible cardinals, this is sort of the usual definition of a strongly inaccessible cardinal, is that it's a strong limit cardinal that's regular. In the context of the axiom of choice, it's equivalent to V kappa being a model of second order set theory. But when P of eta cannot be well ordered, things become more subtle. Okay. So this theorem involves a very deep analysis of the sets of ordinals in L of R, or more generally sets of ordinals under AD, something called the Moskovakis coding lemma, which I think is a really interesting theorem. It's worth looking at. You find yourself interested in AD. But it sort of tells you that sets of ordinals are like a subset of an ordinal eta is roughly as definable as the surjection from the reals onto eta. So sort of get that every subset of eta is definable at the same level as the coding of eta itself by real numbers. And you can think of a surjection from the reals onto an ordinal as a coding of that ordinal by reals. Each ordinal corresponds in the codes to some real or to a bunch of different reals that all code it. Okay, so subsets of eta turn out to be definable at the same level. And this coding lemma it only partially generalizes to L of v lambda plus 1, but it does yield this theorem of Wooden, I think also from the 80s. So if you let theta of L of v lambda plus 1 be the supremum of the ordinals that are coded into v lambda plus 1 in L of v lambda plus 1, then theta is again a strongly inaccessible cardinal. And I want to point out, again, this is another failure of the axiom of choice, in the sense that if under AC, if you let delta be the sup of all ordinals alpha, such that there exists a function from R onto alpha, then delta is actually just a successor cardinal. It's just the successor of the continuum. Whereas here, I'm saying that this cardinal theta in L of R is strongly inaccessible, which means in particular, it's not a successor cardinal. It has to be a limit cardinal. It's a limit of limit cardinals, etc. So these thetas actually turn out to be quite large cardinals. In some sense, they end up reflecting a lot of the strength of the theories of AD and I0. I don't know, when one tries to compute the large cardinal strength of the principal ADL of R, for example, the key ordinal to look at is this ordinal theta of L of R. It turns out to be a very large cardinal inside of inner models. Okay, and just one more example. So this is a strengthening of Solovey's theorem that omega 1 is measurable. Kunin showed that under ADL of R, now L of R, every omega 1 complete filter on an ordinal less than theta can be extended to an omega 1 complete ultrafilter. So this is sort of, so it's an analog of the well-known fact, I can't remember whose theorem this is, that every filter extends to an ultrafilter, Tarski. So that's just an application of Zorn's lemma. Of course, we don't have Zorn's lemma in this context, and in general, in ZFC, you cannot have that every omega 1 complete filter extends to an omega 1 complete ultrafilter. For example, this implies that omega 1 is a measurable cardinal because there's an omega 1 complete non-principal ultrafilter on omega 1. But anyway, so this is a strengthening of Solovey's result. And it turns out that exactly the same result holds in L of v lambda plus 1 for lambda plus. This, I think this is like 2021 or something. Yeah, so a huge amount of the structure theory of L of R is replicated inside of L of v lambda plus 1. And there's really no other known way of generalizing something like AD to larger cardinals. So AD seems like a very specific feature of the real numbers and omega, and yet there is this sort of mysterious structural analog way up at much larger cardinals. So it's a phenomenon that has not really been well explained. Okay, I want to say just a tiny bit about what's past L of v lambda plus 1, since we're talking about the limits of the large cardinal hierarchy in CFC, and I think pretty often it seems from what people say about this that I0 is the end of the story. There's no large cardinals past that, but actually you can go a bit farther. So the first determinacy axiom beyond AD L of R is AD in L of R sharp. So R sharp is sort of the least definable set of reals that's not in L of R. This is a vague definition. So AD in L of R sharp is the next natural determinacy principle. It's significantly stronger than AD L of R. We have that if you have a model of AD, and R is contained in M, and A is in M, but and I guess what I want to say is that and the power set of the reals as computed in M is not contained in L of R, then R sharp exists and L of R sharp satisfies AD. So this sort of gives a more precise version of this claim that R sharp is the least definable set of reals. It's not an L of R. Okay, so there's this canonical set outside of L of R, and you have a stronger theory than AD L of R by asserting AD in L of R sharp. And exactly the same kind of thing happens for L of V lambda plus 1 sharp. I think that tomorrow I'll talk a little bit more about sharps, so you'll get a somewhat better understanding of what this V lambda plus 1 sharp object is, if you don't already know. Okay, but there is this principle beyond I0, and it implies the existence of many I0 cardinals below lambda. It's pretty similar to the kind of reflection that we were getting for the principles dn of lambda that I mentioned. Like if d3 of lambda holds, then, sorry, yeah, that's right. If d3 lambda holds, then lambda is a limit of gamma such that d2 of gamma holds, whatever. So it's the same kind of thing. It's just the next principle beyond I0. And you can push this much farther. So the analogy between L of R and L of V lambda plus 1 can be extended to an analogy between higher determinacy theories and higher embedding principles. I don't want to talk that much about it because I think in a talk where I've tried to even define the axiom of determinacy, it doesn't really make sense to start talking about higher determinacy principles, and all this is a little bit beyond the level I wanted to speak at. So anyway, there's a principle called ADR, which I think is fairly easy to define. It just says all games on reals are determined. So remember, in my definition of a two-player game of perfect information, that each of the players was playing natural numbers, and then they were alternating in order to eventually create a single real number. But the principle ADR, which was first defined by Soloway, instead talks about games where each of the players is playing a real number or an infinite sequence of natural numbers. And it turns out to be significantly stronger than AD, or than AD of an L of R sharp implies R sharp exists, and so on. And there's an analog, or there are several ways of defining analogs of ADR at the level of embeddings from V lambda plus 1 to V lambda plus 1. And the whole theory has sort of been generalized up to there. There are many open questions about these structures, but anyway, all I want to say is that the analogy does not end at an analogy between L of R and L of V lambda plus 1. It actually extends far beyond that. Okay. Still, even though these principles consistent with ZFC do form a very large hierarchy with plenty left to explore that is still not very well understood, there are principles, as I mentioned before, that go beyond all of these, that come from, they're much simpler principles, but the problem is that they're incompatible with choice. So as I said before, in ZFC, assuming the axiom of choice, you can't even have a J from V lambda plus 2 to V lambda plus 2. That's sort of where the large cardinal hierarchy goes off into the choiceless large cardinal hierarchy. And then in ZFC, you spin off into these determinacy-like principles for L of V lambda plus 1 and L of V lambda plus 1 sharp, etc. Okay, so even if you just go slightly into this hierarchy, a J from V lambda plus 3 to V lambda plus 3, you can already prove the consistency of ZFC plus I0 from these principles. So the point of this theorem was, okay, these principles seem to be the large cardinals that are beyond the ZFC large cardinals, but it's not clear, it's not at all obvious that, for example, ZF plus a J from V lambda plus 2 to V lambda plus 2 implies the consistency of ZFC plus I0. The point is, if you have a model of this theory, you have to show that you can produce a model of ZFC with I0. So even though it's not too hard to show that in this theory, you do have a J from L of V lambda plus 1 to L of V lambda plus 1 with lambda equal to, well, whatever. You can get lambda to be equal to this kappa omega of J. You can get this principle, which is what I said was I0. To get that along with the axiom of choice takes significant work. Because here, this theory, you don't have any choice. It could be that the reals aren't even well ordered. So you have to do something to get back to a situation where you have the axiom of choice. Yeah, so even though it's not immediately obvious, it is true that the choiceless large cardinal hypotheses go strictly beyond the ZFC large cardinal hypotheses. So there are principles in the choiceless large cardinal hierarchy, I guess I'll define a couple of them right now, that are known to be strictly stronger than every large cardinal hypothesis compatible with choice that's ever been formulated. Yeah, so the one thing to notice here that might be a little confusing, but it is relevant, is this is what happens with V lambda plus 2. So we know that J from V lambda plus 2 to V lambda plus 2 is a principle that's beyond choice, but I don't know how to show, luckily. So the proof of this theorem does not show that that it's strictly stronger than I0. So we'll talk about that more on a later slide as well. Okay, so this is just the beginning of a hierarchy of principles. So for example, rank Berkeley cardinals. Well, there is a rank Berkeley cardinal if and only if there's some lambda such that for all alpha greater than or equal to lambda, there is a J elementary from V alpha to V alpha. So rank Berkeley cardinal is a slightly more general definition, but the existence of a rank Berkeley cardinal is just equivalent to the existence of non-trivial elementary embeddings from all sufficiently large levels of the cumulative hierarchy to themselves. Okay, so that gives you plenty of j's from v lambda plus 3 to v lambda plus 3 and v lambda plus 17 to v lambda plus 17 and much more. And it's actually still an open question if ZF plus rank Berkeley implies a con of I0. So here, this points to another issue in this theorem, which is a little more mysterious, which is what is DC and why do I need it for this theorem? So DC is a weak choice principle. It's often used in sort of more constructive contexts. It's a version of countable choice. It says it's equivalent to saying that every tree of height omega has a branch, or every relation with no countable descending sequences is well-founded. So it's useful if you have a construction where you're trying to make a choice at each stage and the construction lasts omega stages. DC allows you to run this construction for all infinitely many steps. So yeah, without assuming DC, I don't know if ZF plus a rank Berkeley implies the consistency of I0, even though this should certainly be true. Okay, so also another sort of interesting question is the relationship between rank Berkeley cardinals, which is a principle I think is pretty elegant, versus Reinhardt's principle, an elementary embedding J from the universe of sets to itself. So Reinhardt's principle is at least as strong as rank Berkeley cardinals. So if J is an elementary embedding from V to V, it turns out that kappa omega J is always rank Berkeley. On the other hand, rank Berkeley cardinals, this is a first order principle. So it can't be that the existence of a rank Berkeley cardinal implies this second order principle. But it's conceivable actually that the two principles are equiconsistent, which I think is a nice open problem that could be solved by a graduate student, but maybe can't be solved by me, because I did try a little bit. So yeah, so this is a kind of interesting question, but at least the point I was making was to try to place this rank Berkeley principle within the context of things we've already discussed. So for example, J is from V to V. Okay, and then another interesting, nice principle is called a Berkeley cardinal. So delta is a Berkeley cardinal if whenever you have a transitive set that contains delta, there's an embedding from this set to itself with critical point, well, arbitrarily high between below delta. So I missed a quantifier here for all transitive M containing delta and all alpha less than delta. So Berkeley cardinals are even stronger than rank Berkeley cardinals. They're around the edge of large cardinals, the strongest large cardinals compatible with ZF that anyone has ever studied, although there are ways to strengthen this even more. And the original point of defining a Berkeley cardinal was defined by Wooden to make the following point. It seems impossible, no matter how ridiculously strong you formulate your large cardinal hypotheses, it seems impossible to refute them in ZF. So maybe hard to see why Berkeley cardinals are so much stronger than rank Berkeleys, but they really are. They're strictly stronger than Reinhardt's J's from V to V. And in fact, you can, in ZF alone, show that Berkeley cardinal implies the consistency of, for example, ZFC plus I0. So with no appeal to the axiom of dependent choice or anything. And I'm pretty sure, though I don't know if I ever, if anyone has really checked this, that all the ZFC large cardinals, even the ones beyond I0, are strictly weaker than a Berkeley cardinal. So we have this large cardinal principle, though it's not compatible with choice, that seems to be beyond the entire large cardinal hierarchy. So it raises some serious issues, as I mentioned very early in the talk. How can you get a handle on the consistency of choiceless large cardinals if you can't prove their consistency from any principle that we maybe have more confidence in, like the ZFC large cardinals? So the sort of reasons for believing in the consistency of ZFC large cardinals. I mean, one reason for it is that you can sort of say, well, maybe they're just true. Maybe this is what the universe of sets looks like, has these really big large cardinals, but one is reluctant to say that the choiceless cardinals are true because you also want the axiom of choice to be true. So if you're getting philosophical about the reason for the consistency of large cardinals, it seems hard to justify the choiceless ones. So one way to respond to this, which I think has been attempted by many people, is to refute the choiceless large cardinals in ZF alone. So we know how to refute Reinhardt's embeddings in ZFC, but maybe you can just do that in ZF, and all these philosophical issues are really illusions because all of these principles are just false. So maybe it's not a matter of the axiom of choice. So this is one direction to go, but no one has succeeded in refuting any of the choiceless large cardinals, even if you go beyond a Berkeley. If you formulate anything even halfway reasonable, it's been impossible to refute them. So sort of interesting, but I'll talk, I think, especially tomorrow, but also in the next slide about some attempts that have been made. Okay, and another way one can try to sort of begin to establish the consistency of the choiceless large cardinals is to develop their structure theory. So to try to understand the combinatorics of these cardinals and try to, so I mentioned that it's beginning to seem like you can get a rich and coherent theory out of the choiceless large cardinal principles, but it's not clear what the theory is describing. So as you develop this theory, you get a better handle on what it might be saying, or what kind of universe these choiceless large cardinals could exist in. Yeah, so these are the basically two approaches to trying to understand the consistency of choiceless large cardinals. The sort of funny thing is, in practice, these kind of look the same. Right, as you develop the structure theory and you begin to know more and more about these large cardinals, you're getting closer, if there is a way to refute them, to finding the refutation. Or if you start working on finding the contradiction from choiceless large cardinals, what you really have to do is develop more and more of their theory. So whatever your philosophical approach is, or your, I don't know, this is the difference between these two bullet points is more psychological than something that can really be distinguished in practice. Well, or maybe you'll see. So here's, when we talk about Wooden's attempt to refute the choiceless large cardinal hypotheses. So this comes out of something called the Hod dichotomy theorem. And the background for the Hod dichotomy theorem is that it's a generalization of the Jensen covering lemma. So the Jensen covering lemma is one of the most significant theorems of the 1970s set theory. It says that if you look at the Gödel's constructible universe L, so this is just, we talked about it before, iterated definability through the transfinite. Either L is very close to being the whole universe of sets, or L is very far from being the whole universe of sets. So more specifically, this says that either L has this covering property, that whenever you have a set of ordinals, you can always cover it by a constructible set, so a set that's in L that has the same cardinality up to Aleph1 as the set you started with. So each set is well approximated by a constructible set, or basically L doesn't approximate anything very well. So this says that L doesn't correctly compute any successor cardinals. It thinks that every cardinal is a large cardinal. So for example, this would say that Aleph1, as computed in the true universe, is an inaccessible cardinal in L. So this isn't like this stuff with Aleph1 being measurable in L of R. There, we're talking about the Aleph1 of L of R. This is, the difference here is that L is really far from computing what Aleph1 is. So Aleph1 of L will be some countable ordinal, and so will Aleph2 of L, Aleph3 of L. So its transfinite cardinals are just, they're all wrong. And Aleph1 of V stands way out here. And for example, L of Aleph1 of V is a model of ZFC. So it's closed under, yeah, it's very closed. Okay, so either L is a very rich, very big model, or L is sort of pathetically small. So Wooden's theorem is that, well, let me say something more about this. Under large cardinal axioms, we'll see this kind of thing tomorrow. It's the second bullet point that's true. So if there's a measurable cardinal, for example, then every uncountable cardinal is strongly inaccessible in L. So another example of how large cardinal axioms actually tell you things about fairly small sets. So a measurable cardinal tells you something about constructibility with respect to Aleph1, which is happening way below your measurable cardinal. So if there's a measurable cardinal, then Aleph1 is actually an inaccessible cardinal in L. And it's sort of worse than that for L. L thinks that Aleph1 has basically every large cardinal property. That could possibly hold an L. So if you know these words, for example, Aleph1 is a weakly compact cardinal. It's an ineffable cardinal. I don't know, it's a very big cardinal as far as L knows. And everything that L can define is actually smaller than Aleph1. L is in some sense reduced to the countable in the context of large cardinals. So Wooden's theorem says that the same sort of thing happens above very large cardinals when you replace L with a much bigger inner model, also defined by Gödel, called Hod. So remember, set is OD. Ordinal definable if it is definable over the universe of sets or in the universe of sets from an ordinal. And Hod is the maximum transitive class contained in the OD sets. So it's a model of ZFC, it turns out. So it's sort of an analog of L, but instead of definability in first order definability, which you iterate to build L, you are looking instead at definability over V, or it's really equivalent to looking at second order definability in this context. So Wooden's theorem says that if you have something called an extendable cardinal, it doesn't really matter at this point what extendable means, but it's a very large cardinal. It's somewhere in between one-fold and two-fold super strong in terms of its strength. So if kappa is extendable, then exactly one of the following holds. Either Hod has the same covering property that L did in Jensen's theorem, or every cardinal above kappa, the extendable cardinal, is actually not just strongly inaccessible in Hod, but actually measurable. So it's almost exactly the same dichotomy as before. The analogy is I don't know, pretty strikingly perfect at this point. That this theorem, it hasn't always been such a perfect analogy. This version of the theorem is only about 2019 that this was finally proved. Maybe earlier, maybe let's say 2017. But yeah, so the exact analog of the covering property holds, or an even stronger version of Hod being a small model holds. And everything is relative to this extendable cardinal. So it happens way up high, but still happens. So the question was, okay, we know that large cardinals imply, they give us an answer, they tell us where we are in this Jensen dichotomy theorem. They say that this is true. You can ask which of these two disjuncts is true. So there's a big difference here, though. The difference is that L is sort of an absolute model. You can't change L by any kind of forcing construction, whereas Hod is the farthest thing from absolute. Sort of, you can't pin it down at all. You can't prove any structural properties about Hod, essentially, except that it's a model of the axiom of choice. Whereas we know, or I just mentioned, that L has no measurable cardinals. Hod can satisfy any large cardinal property that can hold in phi. In fact, every large cardinal property known that's consistent with choice is also consistent with the principle that says V is equal to Hod. Okay, so the principle that says every set is ordinal definable. So that there are big differences between these two models, even though there's this analogy between their covering properties. Wooden's Hod conjecture asserts that this analogy is an illusion. It says that assuming large enough cardinals, for example, assuming an extendable cardinal, this first disjunct is actually true. It's actually provable about Hod that this Jensen covering property holds. So the Hod conjecture says that Hod is actually a large model. Okay. So the Hod conjecture it's sort of it's an approach to showing Berkeley cardinals are inconsistent. The point is that there's this theorem of Fudan that if ZF is consistent with a Berkeley cardinal, then ZFC plus extendable cardinals or whatever large cardinals you like really is consistent with the failure of the Hod conjecture. So one can start with a Berkeley cardinal and force not only whatever ZFC large cardinal axiom you want, but also the failure of the Hod conjecture. So this is, I don't know, there are, as usual, two ways of reading this theorem. One is that there's a way to show the consistency of the failure of the Hod conjecture, but you have to start with choiceless cardinals. And the other way to read this theorem is if the Hod conjecture is true or provable, then ZF plus Berkeley cardinals is inconsistent. So the Hod conjecture is made in the context of ZFC. So this gives you a purely ZFC question that if you could solve it, you would refute the existence of Berkeley cardinals in ZF. So that in some way distinguishes this as an approach to the problem of refuting the choiceless cardinals, distinguishes it from the approach that goes through just trying to develop more and more of the combinatorics of the Berkeley cardinals, because this is really a ZFC question. So I want to talk about a little of my work trying to get somewhere close to the Hod conjecture, and I'll talk about this in more detail at some point, maybe give some actual proofs. So the point is to find a version of the Hod conjecture, an equivalent version of it that is just purely about the structure of large cardinals, doesn't say anything about ordinal definability or inner models. So the key notion here is if you have models P and Q, and an ordinal delta in P, and you have two elementary embeddings, J0 and J1 from P to Q, then they're delta similar if one, they both map delta to the same place, and two, if you look at the supremum of where they map ordinals below delta, it's equal again. So it's a resemblance property between these two embeddings. It's a little bit technical, but it is going to be exactly what I need for the theorem I'm about to state. So it says the two embeddings map this ordinal delta to the same place, and their supremum as you range over ordinals below delta is the same. Okay. So the theorem is if you have a supercompact cardinal, then the Hod conjecture is actually equivalent to the statement that given any two delta similar embeddings of a level of V, they must agree on delta. So if you have these two delta similar embeddings, the only way to get delta similarity, so agreement on this supremum and agreement up to the image of delta, is that they actually agreed everywhere below delta. So it's a uniqueness property for elementary embeddings. There's only one embedding on delta that can have these two ordinal characteristics, the soup and the image. But again, this is a sort of, I don't know, it's a structural property of elementary embeddings, the kind of embeddings that you look at all the time in large cardinal theory. And it's saying that in order to establish the Hod conjecture, it is sufficient, but you must show this uniqueness property for embeddings. And you can sort of work on this property. There's a lot you can say about embeddings of V alphas. They have lots of structural properties. So for example, there is an analog of this fact that's just a theorem. So this is for embeddings from V into inner models, this kind of embeddings you look at all the time in large cardinal theory. The theorem is just any two such embeddings have to agree on all the ordinals. Okay, so I've said this before when I talked about this theorem, and I think I only confuse people by saying it, so you might want to just turn off your ears. But for these, any two embeddings from V into an inner model M are in some sense delta similar, where delta is equal to ord. They're ord similar, because they sort of take, there's the soup image of J0 on ord is ord, which is equal to the soup image of J1 on ord. And in some sense, J0 of ord is equal to J1 of ord. But anyway, you do get, that J0 and J1 are delta similar for arbitrarily large ordinals below ord. So, for example, if you had the Hod conjecture, it would be trivial to get this theorem, but actually you can prove this theorem in ZFC alone. I guess it's also worth pointing out that this theorem is a generalization of the original Kunin inconsistency theorem, because in the case when M is equal to V, this is saying that there is a unique elementary embedding, at least up to its action on the ordinals from V into V. But that unique elementary embedding it has to be the identity, right? Because the identity actually is an elementary embedding from V into V. So this says there are no non-trivial elementary embeddings from V to V. But it says much more. It tells you about the structure of arbitrary elementary embeddings. So these are sort of, I don't know, fundamental objects in large cardinal theory, since large cardinals are defined in terms of embeddings from V to M. And this tells you that they're sort of uniquely determined by their target models, something that wasn't really known for a long time. Okay, so I have about 15 more minutes, right?
Yes.
Oh, yeah, so let me point out one more thing about this theorem, which I think is interesting. You can't actually show that there's only one embedding from V to M. You can only show this fact that any two embeddings have to agree on all the ordinals. So it's always possible, if you have a measurable cardinal, to produce by forcing an example of a model of ZFC that thinks there are two embeddings from V into M that don't agree everywhere. But they always have to agree on the ordinals because the embeddings actually come from they're distinct liftings of an embedding of the model you started with before you did the forcing. Okay, so enough about unique embeddings. So yeah, so anyway, this sort of is giving you some hope, gives me some hope that something like the Hod conjecture could be provable, at least if you assume large enough cardinals. Okay, but in the other direction, before I talk about developing the structure theory of large cardinals, I want to sort of give make it, I don't know, muddy the water where it comes to this claim that the choiceless large cardinals cannot be proved consistent from the ZFC traditional large cardinals. So I think this is basically true, at least for choiceless large cardinals at the level of a Berkeley cardinal, because they really do imply the consistency of all the ZFC large cardinals that have been studied. So they can't be proved consistent from something they imply the consistency of. Logic 101. But it's sort of an illusion to think that the ZFC large cardinals are all strictly weaker than the choiceless cardinals. So for example, the very weakest choiceless large cardinal axiom, the very bottom of the hierarchy, was a J from V lambda plus 2 to V lambda plus 2. And I mentioned before that my proof that that J from V lambda plus 3 to V lambda plus 3 gives you common ZFC I0 didn't show the same thing from V lambda plus 2 and several years following the proof. So this is like 2020. Lutzenberg, I recently learned from farmer Schlutzenberg himself that it's pronounced Schlutzenberg. So Schlutzenberg proved that that ZFC plus I0 is equiconsistent actually with ZF plus all this DC lambda principle. So that's a choice principle at the level of lambda. It's similar to lambda AC. So the axiom of choice for families of sets of size lambda, but it's a bit stronger. Plus the existence of an elementary embedding from V lambda plus 2 to V lambda plus 2. So let's see. So farmer, so this proof sort of, I guess the expectation was that a J from V lambda plus 2 to V lambda plus 2 would be a very strong principle, that it would go beyond all the CFC large cardinal axioms. This sort of conjecture that's made many times in Woodin's long paper called Suitable Extender Models. And this theorem totally, totally destroys that belief. It's actually exactly at the level of I0. So the weakest, the first of these choiceless large cardinal axioms is equiconsistent with this well-known and well-studied principle. And so it gives you hope maybe that that other choiceless large cardinal hypotheses at the low end of the hierarchy could also be proved consistent from using the stronger the strengthenings of I0 that I mentioned before, the generalizations of I0 that are sort of these analogs of the axiom of real determinacy, ADR. So it's conceivable now that that there could be a way to prove the consistency of elementary embeddings from V lambda plus 3 to V lambda plus 3, starting with a ZFC large cardinal hypothesis. And it's possible that this kind of thing could reach all the way to, for example, Reinhardt's principle. That's consistent. And so there could be a real way to distinguish between the consistency of something like a Berkeley cardinal, which it's hard to believe could be proved consistent from anything like these principles, and J from V to V, or a rank Berkeley cardinal, which seems more tractable from the ZFC large cardinal axioms. So there's sort of a way forward that goes against the old intuitions that the ZFC large cardinals were below the choiceless large cardinal hierarchy. There's this possibility that actually they're interleaved with the choiceless large cardinal hierarchy. We have these kinds of equiconsistencies that would help establish or give us a better sense of which of these principles are consistent. But still, even the most basic question after d lambda plus 2 to v lambda plus 2 remains open. So I think this is a really great problem. It seems pretty hard, but it could be that there's a not so complicated solution. And that solution could lead all the way to a resolution of the question of the Fudan inconsistency, V to V. So, but Schlüsselberg's theorem already answers many questions related to this. Like, for example, Fudan had shown that there's no j from v to m such that v kappa omega of j plus 1 is contained in m. But Schlüsselberg's theorem shows that, in fact, this principle is consistent in the context of ZF, even with lambda dc, the kappa omega of j dc. At least if you assume I0 is consistent, which I think many people believe. So the strong version of the Fudan bound, actually we know now that that requires the axiom of choice. So it completely explains this, well, not completely, but to a large extent, it explains why the axiom of choice is necessary in Fudan's theorem. It really can't be removed, at least if you want to prove the strong version of Fudan's theorem. So v lambda plus 3 is a natural place to look, both if you want to try to refute the existence, the choiceless large cardinals. Maybe you think, well, it'll happen right at v lambda plus 3, and Farmer just showed v lambda plus 2 is okay, but maybe v lambda plus 3 is where everything falls apart. Or maybe v lambda plus 3 is a nice place to look if you want to extend this theorem and try to show that all the choiceless large cardinals, up to some point at least, are consistent relative to AC large cardinals. Okay, and I had a sketch of the proof of this theorem here, but I think I'm gonna skip over that. I will tell you about the proof of this theorem in much more detail at some point this week. Okay, so moving on to v lambda plus 3, sort of the way I got interested in these principles has to do with a periodicity phenomenon for choiceless large cardinals at the level of v lambda plus 3 and v lambda plus 5. So if you have a limit ordinal lambda, so this is sort of the context where people normally look at elementary embeddings from v lambda plus 1 to v lambda plus 1 in the context of choice. There's a surprising, at least at first sight, surprising fact that any elementary embedding from v lambda plus 1 to itself is actually definable over v lambda plus 1. It's a little weird because J seems like a very complicated object, but it's definable from its restriction to v lambda. The reason is if you have an element of v lambda plus 1, the only place it could be sent by J is to the union of where all its little fragments below v lambda are sent by its restriction to v lambda. So that gives you a definition, and the definition is really makes sense in the structure of v lambda plus 1, since I itself is an element of v lambda plus 1. So it gives you a definition of J over v lambda plus 1. But on the other hand, if J is an embedding from v lambda plus 2 to v lambda plus 2, and now we're in the context of ZF, because otherwise this is a vacuous statement. We know that in ZFC there cannot be any such embeddings. But here's a difference between them, which it doesn't use any choice. Difference is such a J is never definable from parameters over v lambda plus 2. So this is giving us a totally choice-free fact that distinguishes between the embeddings that we're more used to from the ZFC setting and the embeddings at the very bottom of the choiceless large cardinal hierarchy. Farmer Schlutzenberg raised the question of whether for n greater than 3 this persists. Are all the choiceless type embeddings undefinable over their levels? So if you have a j from v lambda plus n to v lambda plus n, can it be definable over v lambda plus n? It seems, based on the way these things usually work in large cardinals, one would sort of, I don't know, I certainly expected that that the answer to this question would be yes, that no j could be definable, because sort of like when you get this kind of behavior, you don't expect it to start changing again. So something became undefinable at the v lambda plus 2 level. The chances are you can't have a definable one over v lambda plus 3. But actually the answer is totally different. So it turns out, Farmer and I proved this theorem independently. It turns out that if you have a j from v alpha to v alpha, j is definable over v alpha if and only if alpha is odd. So the odd ordinals are like, okay, lambda is a limit ordinal, we say it's even, lambda plus 1 is odd, lambda plus 2 is even, lambda plus 3 is odd. So for example, any elementary embedding from v lambda plus 3 to v lambda plus 3 is definable over v lambda plus 3 from a parameter. The parameter is essentially j restriction v lambda plus 2, although you have to be a little careful because technically j restricted to v lambda plus 2 is not an element of v lambda plus 3.
But in theorem, from v lambda plus alpha to
Sorry,
v
can you say that again?
plus alpha. So in the theorem, j, is it supposed to be v from a v sub lambda plus alpha into v?
So
it's
one
fine.
way,
Okay, I realize.
another way you could say this theorem, yeah, is that if j goes from v lambda plus n to v lambda plus n, where lambda is a limit, then j is definable over v lambda plus n if n is odd. But the point is just, point here is just that the answer to this question is no. And in fact, the structure of definability of embeddings begins to alternate based on even and odd as you enter the choiceless hierarchy. So what happens is that the theory of elementary embeddings from v lambda plus 1 to v lambda plus 1 that we know and love from the ZFC context turns out to generalize to the theory of elementary embeddings from v lambda plus 3 to v lambda plus 3. And so, for example, I0 generalizes to give a theory for L of v lambda plus 3 and much more. But basically what's going on is that you can uniformly analyze these embeddings using the analysis that has already been done by people like Martin and Laver in ZFC by just trying to lift that theory to all the odd levels.
I see. Thanks.
So it's a bit like the way the axiom of determinacy or projective determinacy allows you to lift the theory of Borel sets and sigma 1, 2 sets to the projective hierarchy. So to sigma 1, 4 sets and sigma 1, 6 and so on.
Thanks. Yes.
Yeah. Thanks for the question. I'm relying on you for questions now. Okay. So let me say a little bit about the structure theory under ZF of plus choiceless large cardinals. So cardinal is sigma 2 reflecting if V kappa is an elementary substructure, a sigma 2 elementary substructure of V. Another way to say this, well, that should be good enough. Hopefully you know about the Levy hierarchy. So a key fact in trying to develop, well, here's one way to say it. A big problem if you're trying to develop a theory of choiceless large cardinals is that you're not allowed to use the axiom of choice. And it can be very annoying not to have the axiom of choice because many arguments that come to mind require it. And many basic things that feel like they should be true, you can't do anything. And so for a very long time, I would say up to like 2020 or something, almost no combinatorial consequences of Reinhardt's principle that there's a J from V to V were known. The reason is just couldn't do anything without AC. And so some much stronger principles were known to have some interesting combinatorial consequences. So for example, Coutelot in her thesis proved lots of quite interesting combinatorics from the existence of a limit of Berkeley's and extendables or something, some very, very strong principle, way beyond this J from V to V. And the way it worked was you would use the large cardinal axioms along with some techniques due to Wooden to actually force fragments of the axiom of choice to be true. So you would move into a generic extension where you have some fragment of choice, and then you could use the axiom of choice there to prove some combinatorial facts, and then you could pull that back down into the old universe of sets and say by absoluteness, this combinatorial fact was already true. So it's a kind of meta-mathematical way of simulating the axiom of choice. And the new discovery that allows a lot of what was done to actually just be done from the principles like J from V to V is that you can simulate the axiom of choice, in fact, just using the large cardinals that you get from a J from V to V. And you can do this in a sort of combinatorial way that doesn't involve passing to generic extensions or metamathematics. Actually, it's an open question whether you can force any fragments of the axiom of choice starting with a J from V to V, but you get something that's a lot like the axiom of choice. And that's this well-ordered collection lemma. So what is the well-ordered collection lemma? It says, if lambda is a rank Berkeley cardinal and you have a singular sigma 2 reflecting cardinal kappa above lambda. So by the reflection theorem, there's a proper class of sigma 2 reflecting cardinals above, I mean, just in general. And so many of them are singular. I only state singular here because it makes it a little simpler to state the conclusion. Then you have this version of AC. If you have a family of non-empty sets of size less than or equal to your sigma 2 reflecting cardinal kappa, you can find V kappa indexed family of sets, a V kappa indexed family that intersects all the sets. So if you could find the axiom of choice would tell you that you can pick an element from each set. This says that there's a not so large family of sets, just of the same V kappa size as your family you started with, that picks maybe more than one element from each of the sets, but it has at least one element of each set. So it really is an analog of AC, but it's being proved using the rank Berkeley properties. So it's not true at all that in ZF, a singular sigma 2 reflecting cardinal has this well-ordered collection lemma. It's really very much necessary for this theorem that we started with the rank Berkeley. Okay, so what can you do with the well-ordered collection lemma? Well, I wanted to say, yeah, if I had asserted the existence of this set AX where X ranged in kappa, this would be equivalent to asserting the axiom of choice for families of sets of size kappa. And that is just false once you get above a rank Berkeley cardinal. Oh yeah, and I very briefly said what a rank Berkeley cardinal was before, but if you want, you can just think of this lambda as being equal to kappa omega of J, when J is an elementary embedding from V to V. So if you can't remember what a rank Berkeley cardinal was, you can weaken the theorem to this. And this still gives you a non-trivial theorem. It's useful. So as I mentioned, if you have a J from V to V, then its kappa omega is always a rank Berkeley cardinal. Okay, what can you do from this? Well, for example, as an example of how little had been known about choiceless large cardinals at this level, there was this question due to Aspero. If there is a J from V to V, must there be a proper class of regular cardinals? So if you're familiar with the pathologies of the theory ZF, you may have heard of Giddick's famous theorem from, I guess, the 1980s. Giddick produced a model of ZF in which there are no regular uncountable cardinals. It's totally bizarre. So in the context of ZF, successor cardinals do not have to be regular, but what was the hard part of the problem is to make every successor cardinal singular and yet have a model that still satisfies all of the ZF axioms. So Aspero's question is whether that kind of thing could happen in the context where you have a J from V to V. So it seems totally impossible to produce a model like that. Well, oh, I meant to circle something, but instead I erased it. Whatever. Okay, so the theorem is if you have a rank Berkeley cardinal, then every sigma 2 reflecting cardinal above it is either regular or has a regular successor. And the point is, if kappa is singular, you can apply this fact to prove the fact is strong enough to tell you that the successor is regular. Otherwise, kappa is just regular. Okay, so it's the sigma 2 reflecting cardinals give you a proper class of regular cardinals. And they give you actually much more than that. So for example, if you have any sigma 2 reflecting cardinal kappa, then the set of kappa complete ultrafilters on ordinals can be well ordered. So any set of kappa complete ultrafilters on ordinals can be well ordered. So the idea is you look at the set, for example, beta kappa of any ordinal eta, which is just all the kappa complete UFs on eta, and you can find a well ordering for this set. This is, I think, strange at first sight, because you might think, well, ultrafilters are sort of the canonical example of something that is undefinable in some sense. At least that's how people typically feel about ultrafilters on omega. But yet we have these well orderings that we're constructing in the context of ZF and these choiceless principles of kappa complete ultrafilters. So it's sort of a surprising thing, and it turns out to be very, very useful. And it's analogous to the situation with AD, which implies any set of omega-1 complete ultrafilters on ordinals. Can be well ordered. And I guess AD also implies that every ultrafilter on an ordinal is omega-1 complete, so I can just say it this way. Okay, so this is at least true in L of R if you assume AD L of R. Okay. So we have some strange confluence of the two theories. Another thing you can do is, and I think this is pretty surprising too, is if you have any sigma 2 reflecting cardinal above a rank Berkeley, then every kappa complete filter on an ordinal can be extended to a kappa complete ultrafilter. So this is again analogous to this AD fact that every omega-1 complete filter on an ordinal less than theta can be extended to an omega-1 complete ultrafilter, which I mentioned before after the break, so you should still remember it. But what's weird here, if you're familiar with large cardinals, is that in the usual context of large cardinals, this property, every kappa complete filter can be extended to a kappa complete ultrafilter, is a large cardinal property. It's just strong compactness. So kappa is a strongly compact cardinal if and only if this holds. So it's a very strong large cardinal principle. But in this case, I'm saying that it actually holds for every sigma 2 reflecting cardinal. And the sigma 2 reflecting cardinals can just be singular. So it's quite unexpected, I think, from the ZFC intuitions that the sigma 2 reflecting cardinals would actually satisfy strong compactness. So it's a reflection of how badly the axiom of choice fails in the context of rank Berkeley cardinals. But also it implies if kappa is sigma 2 reflecting, either kappa or kappa plus, it's not just regular, but actually measurable. So in particular, if kappa is a singular sigma 2 reflecting cardinal, which, you know, those kinds of cardinals do exist under ZFC, then kappa plus is always measurable. So we have lots of successors of singular cardinals that are measurable in the context of rank Berkeley cardinals. So it's a major failure of the axiom of choice. Okay, I don't have too much time. So
yeah, so Gabe, we should end at 15.
Yeah,
So
in 2 minutes. The presentation is almost over. Don't worry.
Yeah, okay.
Let me see. So let me see. I just wanted to talk about, so I might go over time by a minute or so. I'm sorry about that.
It should be your time. I think 10 o'clock is the. It should be in the 10 o'clock. Your time, right?
Oh, I should have ended at 10 o'clock?
Yeah.
Oh no.
Yeah. Oh, okay.
So I've gone over time.
Sorry.
I can't believe it though. I have, there are only 30 slides here. So I'm always shocked that they can go, I can make them last arbitrarily long. I've used these slides before. No matter how long of a time I'm given to talk, the slides last longer than that. It's some kind of magic. Okay, so let me just tell you what we're going to talk about over the next few days. Sorry, I forgot that we were ending at 10. Next time, if I go this far over time, just remind me, because I really thought I had until 10:15. Okay, so sorry everyone. So the plan for the next few lectures is tomorrow I'm going to talk in more detail about measurable cardinals and constructibility. So this Jensen dichotomy theorem I mentioned before, and then about Wooden's Hod conjecture and ordinal definability and the Hod dichotomy theorem, and maybe about the unique embeddings theorems that I mentioned. So this is this approach to trying to refute Berkeley cardinals in CF. And then in the next few lectures, I'm going to talk about this theorem on the periodicity of embeddings. So this is the theorem of mine with Schlutzenberg that for example, a J from V lambda plus 3 to V lambda plus 3, lambda is a limit ordinal, is definable over V lambda plus 3. Okay, then lecture 4 is going to be about simulating the axiom of choice, so that these things I was just talking about, so the sigma 2 reflecting cardinals and well-ordered collection lemma. And then lecture 5 is about the measures on ordinals, and then this theta alpha sequence. So the theta alpha sequence, it's a generalization of this ordinal theta from the context of determinacy, or I0. It's the supremum of all ordinals eta, such that for some beta less than alpha, there is a surjection from V beta onto eta. And it turns out that the periodicity features that we had here for the structure of elementary embeddings can be translated into combinatorial features of these cardinals theta alpha. And so the sort of the deepest consequences I know of the J's from V to V have to do with the fact that these theta alphas, that their properties alternate depending on whether alpha is even or odd. It's so here we have this periodicity phenomenon, but it's sort of metamathematical. It has to do with definability and elementarity. But this is a purely combinatorial feature of the cardinal arithmetic in the context of choiceless large cardinals. That's again periodic. So this kind of thing is actually, I think that it is without precedent in set theory to have fully combinatorial periodicity phenomenon. In the context of AD, it's always related to definability. At some level, there's always sort of sigma n definability coming up. And there the periodicity is sort of built into the formulas. But here it's just periodicity based on ranks. Okay, so that's the plan for the next few lectures. It'll go up on the website once I send everything in. So thanks for listening, and sorry I went so far over. I would have just stopped if I had known that I was supposed to stop.
Yeah, I mean, it's a long course. You have 5 days. You need to keep energy. So thank you. Thank you.
Yeah, and so there are some exercises that I'll send out, or that they'll be put up on the website, I guess.
Yeah.
They basically are about large cardinals in the context of AC, and I think some of them are pretty challenging, and some of them are just review of things that you can find all the answers in a book. So okay. We'll see how it goes. And if you have questions about the problems, then you can email me, and I will respond. I promise.
I'm sorry.
Okay.
I'm sorry. A quick question. Can we have the slides of today's lecture?
Yeah, of course. Those will be online too.
All right.
So you can email.
Yeah,
you can email to me, and we put it on the website. Right?
Yeah.
Okay.
Mm-hmm.
Okay. Thank you.
Well, thanks for attending.
Okay. That's all for today. Thank you. And